So I'm trying to learn, or I'm trying to escape Arduino and learn the STM32. So this is my kind of first project that I'm not, copying code from tutorials. And it's, as you can see, it's two 7-segment displays. They are multiplexed. So far it's pretty slow, obviously, but that's just for the purpose of showing you, so we can see it. So this is the kind of circuit. There are the transistors, and yeah, pretty straightforward, I think. The code, so the multiplexing itself is done by interrupts, or one interrupt generated by a timer, and the period is 500 milliseconds. So I'm using CubeMX to kind of help me out. If you don't know what CubeMX is, it generates code for you. The initialization, the setup and stuff, so you can start coding. It's kind of it helps when you are coming from an Arduino and you're trying to learn all this and this C and its in its glory. Yeah, can be kind of overwhelming. So this is the main loop, which is displaying the numbers, and I've got my function display right, which is right here. So that's pretty straightforward. You got a byte on the input, and you kind of tear it apart and send it to individual pins. And this is, as you can see, that the numbering and all this stuff kind of lines up, because I'm pretty sure you can somehow shift the whole byte into the GPIO port, but I haven't really figured out how. So yeah, I haven't really looked into it. This works, and it's simple and straightforward. You just take the first byte, the first bit, and if it's 1, then you set the GPIO pin 1, or then you set the GPIO pin. If it's not, you just leave it, and all the way to the bit 7, and I don't use the bit 8. And this is these are the arrays that actually define the individual numbers, and yeah, and these are just segments. And the interrupt, where is it? Here, I just toggle those 2 pins. Sorry, yeah. And that's the pre-made function. You can find them in the list of the functions, and it's all generated by CubeMX, or the whole libraries, of course. So now I'm going to try to speed things up a little bit and see whether it actually works. So I increased the period of the timer, and now obviously we have to move the display right to the interrupt, because it's switching so quickly. You have to actually write the GPIO pins that are connected to the individual segments, or at least I think that that's the case. And I've got a predefined byte which is called display buffer. Yep. So we're going to feed that into the display right when the GPIO event happens. So that should work. Now we'll just change this to yeah, that should work, I guess. So we can try to compile it and let's see whether it works. It's not. So let's reset it, and it's doing exactly what I thought it should. So this works. Now what if we want to display different characters on the display, on each display? So I'm going to try to modify the code to do exactly that. So that only maybe took like 3 minutes, very simple. So as you can see now, they are counting, one is counting the normal way, one is counting backwards. So they are kind of mirrored, let's say. So how I did that? So this is the main loop again, and I just created another this buffer, and of course this is how you get the inverted counting, and I increase the period so we can see what it's actually doing. Now I haven't really changed anything other than defined another display buffer, but I changed the interrupt procedure quite a bit. So I also created this multiplex variable or integer or whatever, and it basically just turns on the correct display and displays its display buffer, or writes the display buffer, and of course resets it when the multiplex is higher than 1. So we could actually expand this very easily just by adding more of these lines. It's pretty straightforward, but I don't need more. This is the basic principle of multiplexing. Yeah, let's just average this out. Yeah, beautiful. So now we can see properly the waveform, and it's actually pretty nice. It's instant. We can measure using cursors. Right, oh, wrong knob. Yep. Okay, so it's a little slower actually. Interesting. I'm using the internal oscillator. I wonder whether that has anything to do with that. Because yeah, I was expecting 200 Hertz and I'm getting 170 Hertz. Of course, I'm not really expecting the thing to, you know, it's 900 microseconds delay, or 900 microseconds off, essentially. Interesting. So I'm going to try to switch to the external oscillator, and I'm also running at 8 megahertz. So maybe we could try increasing the clock speed to see whether it changes anything. So so let's change the cursors. Okay, I could probably use the, so it increased a little bit, but it's nothing, it's still not 200. So yeah, I'm guessing the reason is that the interrupt just takes some time. Also the GPIO write, of course, takes some time. So yeah, I think if you were to just toggle a pin on an interrupt, you could get pretty accurate frequency out of it, like expected frequency. But in this case it's doing quite a lot, the interrupt, so yeah, this is to be expected. But still, it's not a problem because the display looks fine and everything. I could actually, just for fun, I have a slow motion. So let's see if we record a little bit of this, and so you can see them flashing, alternating in the slow motion, because this is 480 Hertz and 480 FPS, and the multiplex is running at exactly 183 Hertz. So that's about it. Now I'm going to try to figure out how to drive this, because it's not as simple as driving this. Because if you take a look at the datasheet, you can see in the you can see that it's wired up. There's quite a lot of LEDs in series. 4 LEDs or 2 LEDs in parallel, and then 4 of these in series. So that would be about around 12 volts to drive them. So this is what I got so far. So this is the display. Obviously only one segment is connected, and it's copying, it's connected to the same pin as the bottom display of this, the bottom segment of this display, sorry. So it's doing exactly what it's supposed to. I'm probably grossly overdriving the STM32 pin. As you can see, the bottom segment is quite a bit dimmer than the other ones, but it's alright, I hope. We are running at only 15 milliamps. According to the datasheet, the LEDs should be able to take about 150 milliamps peak. So that's for, of course, matrix or these multiplex situations where you need to increase the peak current to get the same brightness out of these LEDs. But this display is actually really bright if you crank up the voltage or the current, and it shouldn't be a problem for indoor use at all. Anyways, to show you a little bit more of the circuit, so this is the common driver. So basically this display is wired in, well, actually let me show you let me show you the datasheet. So it's this one, and so the positives are command up, and you control the negative connections, which is good, because now this is all you need to control one of those negative connections. It's just one transistor and the base resistor, and this is what you need to control the command positive. It's a PNP transistor and an NPN transistor, which is driving the PNP transistor. And fortunately we only need 2 of these, because we will have 2 displays. So that's the plan. I don't have big enough board to fit all of this stuff onto, so I think I'm going to just glue them together like this. Got a piece of, I don't know what this is, it's like, yeah, whatever. So I'll probably do the picture frame approach, maybe. so that might be fun. I think this is all I need to fit those drivers on, and the STM kind of, because I only need this row, I selected such pins that I only need this header row, so this one can be free floating. Alright, so the board is finished, as you can see. It looks something like this. I really didn't have anything larger, but it works alright. It's enough for this. It's big enough. So yeah, I found out that I don't have any voltage regulators, so it has to be powered from the PC for this moment, but I'm going to get some. So now I just tested it, it works. I'm waiting for my hot glue gun to heat up, so I'm going to glue these together to make it kind of more self-contained, so the wires aren't everywhere. Anyways, so I'll show you how I wire these up. It's pretty straightforward. I just solder directly to them. So basically all the segment pins are paralleled, and then these are the common positives that I routed to over here, which you might recognize those transistors from before. Those are the power transistors, the PMP ones. Can't really see. Yeah, I hope you can see everything. This resistor is for the dot, because according to the data sheet, the dot is only 2 LEDs in series, so it's going to require different current and different voltage, so completely different value of resistor. And of course you don't want your dot to be dimmer or brighter than all the rest of the digits, so that's why I kind of added this socket to make the resistor variable, essentially. Alright, so this is what it looks like right now. I've made many modifications and added many things. So for example, this temperature sensor, it's a LM75. It's I2C temperature sensor. Because I couldn't get the DHT11 to work, so this works just fine. I even wrote the sketch myself, so it's not really hard to control this. If you want to get started with serial communication, I highly recommend this one because the datasheet is well written, and yeah, it's really simple device. You can learn how to use I2C on it. Overall, here nothing really changed other than the pull-up resistors. Zoom in so you can see. So there are the pull-up resistors. Change the power supply, or I used to have a linear regulator here, but that would overheat pretty quickly, so I added the switching one. I just added this photoresistor, so it can now change brightness based on the ambient lighting. So let me show you. If I dim down the lights, it's going to dim. It's going to become dimmer, and this is all the way up. But it can go a lot dimmer than this. Yeah. So you can see the flicker. I'll show you how I did the dimming in just a second. Yeah, this kind of fell off, but it's alright. Yeah, whatever, so it works. If I heat up the sensor, it's going to count up. If I spray a little bit, it's going to... So yeah, let me show you what it does. Okay, so this is below -10 degrees, and now it's going to go up. So it's showing the minus symbol. And as the sensor kind of heats up, slowly. Yeah, it's really cold. You can see the ghosting here. I tried to, it's much better than it was before. But it's still not perfect. It's mostly due to the fact that the transistor, the high side transistor that I'm using, kind of doesn't open all the way. So there's quite a lot of leakage visible on the display. You can see this ghosting. It's much worse when I increase the brightness. As you can see, yeah, this is pretty bad. I'm going to fix this by replacing those transistors with MOSFETs, which shouldn't have this problem. Those transistors aren't really good, aren't really great transistors, so I don't have any P-channel MOSFETs right now, so I have to wait and buy some. Dot is much worse with the ghosting. Probably because it has much higher resistor, like current limiting resistor. So I guess like maybe a shunt resistor would help mitigate this, like putting a resistor in parallel with the LED, because this is obviously some kind of capacitive residue, I would say. Maybe. Anyways, let me show you the code. So, I2C communication, pretty straightforward. This is actually converting the data to something sensible. So I actually found this in an example for this IC because I couldn't really figure it out on my own. Let me actually bring up the datasheet for it. So yeah, this is the datasheet, and this is the chart. Oh yeah, let me not drop the camera. This is the chart, the temperature chart, what corresponds to what. So as you can see, this is pretty non-standard, or I don't know, like 9-bit value. How often do you come across that? So the least significant bit means half a degrees increment. So yeah, you can see this clearly. And yeah, it kind of goes back to front when the temperature is negative. It works, I guess, but it's not really intuitive. So that's the only thing I had to like Google. Yeah, show you the whole thing. I might link the GitHub example down in the description. It's like really long code that you can use every feature of the chip with, but really it's not written using HAL, but that doesn't really matter for in this case. It's moving on. So we are getting into the brightness, but before we go there, this is like my really easy way of dealing with like it's not really averaging, but it kind of does the same effect. kind of has the same effect. It mitigates the issue where the sensor is jumping in between like 20 degrees and 20.5 degrees, and the display is constantly flashing and it's annoying. So this is essentially getting rid of that issue. I've got it comment out for now because I wanted to show you the response to the freeze spray. Of course, but you would have to, well, the readings wouldn't get stable enough to display on the thing, but in normal use this is not a problem. Of course you want stable readings, you don't want the display to flash all the time. Okay, so yeah, this is the ADC, getting the ADC, the value of photoresistor, photoresistor. So again, pretty straightforward using HAL, and this is the conversion. As you can see, fine-tuned. I spent quite a lot of time coming up with these values, so the response to light is optimal. As you can see, it's kind of squared. Yeah, it works pretty well actually now that it's done, but it took a long time to get here. And these are just the end stops for the brightness. Of course, you don't want the value to go negative or something. And let me show you the actual interrupt code. Here we go. So I modified it a bit. Let's make it a little more kind of readable. So of course it firstly resets the pins. Reset essentially turns off power to both displays. Then, depending on the multiplex value, which is constantly incrementing with each interrupt, so it's going to show when the value is 0, it's going to turn on the first display and display the stuff that it should display. Then the next interrupt happens, it's going to turn off both displays. Let's say we have a brightness value of 4. Okay, so that's where the multiplex value resets to 0. So if the brightness is 4, then when the multiplex is 0, it's going to show the first display. Then it's going to, on the second time it interrupts, it's going to just clear both displays. Because this isn't true yet, because if we have number 4, then that would be 3, so you need to wait. So then it gets to number 3, it's going to display this, the second display, and then it's going to overflow and it's going to reset. So if you increase this brightness value, it's essentially increasing the gap in between the display refreshes. So the full brightness would be at brightness 1. So that's where this is constantly, when the multiplex is 1, it's going to show the first display. When the multiplex is 2, it's going to, or no, sorry, multiplex is 0, it's going to show the first display. Multiplex is 1, it's going to show the second display, then it's going to reset and all over again. So at first I had it so that the multiplex, so it would be like this, just like this, you know, so that was the default. But in order to mitigate that problem with ghosting, well, it didn't really solve it, but it helped a lot, was to kind of put it's logical, of course. Yeah, you can space it out so it has more time to kind of discharge all those capacitive residues and stuff. Or perhaps the phosphor in the LEDs is doing this, but I doubt that. But it could be that as well. But yeah, so far it seems like it's electrical, because it's kind of obvious that the dot has the ghosting problem while the segments don't. And the dot has like 20 times higher resistor value, so it takes more time to discharge that. So yeah, the MOSFETs might solve that, and some bleeding resistors probably could also like help. Yeah, so that's about it for the code. Really straightforward. I had to also, yeah, that's another thing I had to modify. Was this display integer thing that we had before. So before it was just this, and then the display buffers. So I had to modify it so it would understand negative values and, you know, show everything correctly. So this is just big mess of ifs, and yeah, but it works. Very visible display, this one. So it's up on the shelf, clearly visible, and it adjusts to the lighting. You can probably see it change the brightness. If you like take a little torch, shine light at it. Yeah, compensates. If you get closer, it gets brighter. Yeah, it works pretty well actually. So another little project is complete. Let's move on to playing with NRF24s, because why not?